Good morning, everyone. So how was your homework yesterday?
What did you say? I couldn't hear you. My internet lagged out for a second.
How was your homework yesterday? Did you hear me now or not?
Okay,
yet?
yes, sir. All right, yes, it did. Thank you.
Great, thanks. All right, so while you guys put your homework, your questions on chat that I imagine you should had some difficulties with, I will remind you the main series we did yesterday, and I'm going to do 2 more, and then I will take up your question. But in the meantime, you guys feel comfortable to put them. So yesterday we talked about the general formula for basically the power series of any function, and we call it the Taylor series. At a point A, you guys should have this written down so you don't have to worry to write it. And the idea that most of the function we have, we know that like exponential, the sine, the logarithm, as long as the derivative at a point A, all the derivative exists, then every function is equal to its Taylor series. So that's the Taylor series, which is the series whose partial sums are the Taylor polynomial that we worked with before. So this is my series. And the equality hold, so this is equal, equality hold for all x's where the series converge, for all x's where the Taylor series converge. Converge. Okay. Now, the 2 series we did yesterday, which are, seems kind of crooked, I don't know why. All right. The 2 series we did yesterday was e to the x. Okay, and we said that e to the x could be written like that. So that's the Taylor series of the e to the x. So on. So it's sigma x to the n over n factorial, n equals 0 to infinity. And this equality hold, it means e to the x is equal for all values of x. Means no matter what x you put in this series, no matter what x you put here, this equality hold. So that's the first one we saw. So for example, suppose I put 1 here for x, and I put 1 here for the sum and the idea that if you keep adding those terms, you actually get the number e. So e sometimes could be defined, some book define the number e, which is this bizarre number, this mysterious number we use, as nothing more than the sum of the terms of this series. So basically, if we actually pick our calculator, which should be somewhere here, okay, I calculate it and start adding those terms, we get to e. So let me add a little bit. 1 plus 1, just out of curiosity, 2 plus 1 over 2 factorial, plus, let us say, add 1 over 3 factorial, which is a 6, plus 1 over 4 factorial, which is 1 over 24. As you realize, we're getting very, very close to e. And e, if you remember, e, the number e, is 2.71. So if I start adding those terms, we actually get to the number e. Now I've only added the first 4 terms. If I start adding a little bit more, I really reach the number e. And some people use this. So if I want the number e, if you want for as many decimal places as I want, I can keep adding terms to get closer and closer to the actual value of e. Right. The second series of importance for us was the Sine X. And the Sine X was its Taylor series, x minus, it only kept the odd plus x5 over 5 factorial, x7 over 7 factorial, and so on. And in sigma notation, because it only involved the odd powers, it was to the n minus plus 1 over the quantity to n plus 1 factorial, and that is the minus 1 to the n equal 0 to infinity. And this is for all x also. And how does the approximation work? If x is close to 0, we need basically few terms to approximate sine x. So the first few terms will approximate sine x1. As we get farther away from 0, we need more and more terms to approximate the sine. That's really how this one would work. Now, the other two important series that I would like to do before I take all your question is the cosine x. What's the power series of cosine x? Because that's a very important function, and the ln of 1 plus x. Okay, so we're going to do the cosine, the ln, and then I proceed. So Taylor series of cosine or Maclaurin series. What's the difference between Taylor and Maclaurin?
Maclaurin, the center is always at 0.
Exactly. Maclaurin, it means Taylor, where A equal to 0. Oops. You guys, when you don't see, let me know. All right, so let us see the Maclaurin series of cosine. So the formula would be, we need f of 0, f prime of 0x, the third derivative at 0 over 3 factorial x cubed, and we keep going. So that's the Maclaurin series. So to find it, I need to find all the terms. All right, so let's do that. And this is like yesterday, we stop whenever you think we should stop. So f of 0 is cosine of 0, which is 1. F prime minus the sine. So at 0, it is 0. F double prime, it's minus cosine. So f double prime at 0 is minus 1. And then the third derivative is minus, so it's going to be the sine. So the third derivative at 0 is 0. And now the values are going to start, when I compute the fourth derivative, I'm going to get the cosine. And now we start to, it's going to be 1. And then now, of course, we have to start like we started yesterday. So the pattern was 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1. So let's see what the power series is going to be. So the cosine x is f of 0 is 1. F prime is 0. So there is no coefficient of x. F double prime is minus 1 over 2 factorial x squared. So that's the quadratic. You can think of this as the quadratic approximation. The third derivative is 0. The fourth derivative, x4. The fifth is 0. The sixth derivative, that's the patterns that's going to be built up, and so on and so forth. So that's the cosine of x. And in sigma notation, it will be. It alternates. Only even power are in the picture. And this should be, those are the same. So that's the quantity to n factorial. N equals 0 to infinity. The interval of convergence, this series, because of the 2n factorial in the denominator, this will work also for all x. And another important series is the cosine. So the cosine, if you want to approximate it near 0, I can use 1 over minus a half x squared. So that's the best approximation I have for cosine. If I need better and better, I can start add more and more terms to the series.
I have a question.
Yes, please.
So 2n x over 2n works when you're trying to keep even numbers. And 2n plus 1 is for when you need to keep odd numbers.
Exactly. Yeah, because every even number is, how could it be written? So if I take any even number, it's divisible by 2, right?
Yes.
Yeah. So if 6 is 2 times 3, 4, 2 times 2. Okay. And so 8, 2 times 4. So every even, you can write it as 2 times something, 2 times something. So I'm looking at this as 2 times 1, 2 times 2, that's the n. 2 times 3, 3 is n. 2 times 4, 2 times 5, and so on and so forth. Now odd or even, like 5, is the 4 plus 1. So it's 2n plus 1. 7 is 2 times 6 plus 1. It means 2 times 3 plus 1. Does it make any sense?
Yes. Thank you.
Okay, now there is one more I would like to do, and then it's the ln. ln of 1 plus x. ln is again problematic function. So we're going to do the power series of ln. Now, let me ask you a question, see if you guys can answer me. If I take ln of x by itself, can I talk about the Maclaurin of ln of x? Do you think this makes any sense? You don't have to write, but does this really make any sense? What's really the problem with writing the Maclaurin?
Because if the Taylor is at 0, ln of 0 does not exist.
Absolutely. None of them exist. F of 0 doesn't exist. F prime of 0 even does not exist. So ln of x basically, and graphically, this is the ln of x. The ln of x goes like that. Okay. So there is no way I can approximate it by anything near 0 because it's not defined near 0 anyway. So we don't really talk about the Maclaurin of ln's. If I have the ln of x, if I want to approximate it by polynomial, I can approximate it near a point, like near 1. So I need to use the Taylor at a center at a equal to 1. There is no way I can approximate it near 0 because it doesn't really make sense. So if I want to approximate it at 1, but this will be one of your homework to do that. If I want to approximate it near 1, and then I can start using the Taylor polynomial near 1. I can approximate by polynomial. I can do it near 1. If I'm interested in the approximation at 1. If I want to interested in the approximation at 2, I can do Taylor polynomial at a equal to 2. But that's a function where I cannot do at 0 because it doesn't really make sense at 0. So what I'm going to do now is not ln of x. I'm going to do ln of 1 plus x, which is definitely defined at 0, and it has no problem whatsoever. And the question is, what's its power series representation? Or Taylor. Those mean verbatim the same thing. So there are basic series that usually in a face-to-face class, I almost ask the student to memorize because they are basic one. So ln of 1 plus x is one of those. So we're going to find the Maclaurin series of f of x equal ln of 1 plus x. Okay. So again, we have to go after the derivatives and proceed. So my function is ln of 1 plus x. And this will be a little bit harder, but so f of 0 is going to be ln of 1, which is 0. And then I'm going to take the first derivative, f prime. It's 1 over 1 plus x. So f prime at 0 is equal to 1. Now f double prime. Of course, I have 1 over 1 plus x. So the easy way to find the derivative is rewrite this to the power minus 1 to make differentiation easier. I will have minus 1 plus x to the minus 2. And here I will have a minus 1. Now, usually, we try to look for a pattern eventually when we're finding those derivatives. Otherwise, I have to keep on forever. So I will minus say plus 2, 1 plus x to the power minus 3. So the third derivative is minus 2. So far, I know none of us see any pattern whatsoever. We have to keep going to start realizing if there is anything showing up. Now, the fourth derivative is equal to minus is a plus, 2 times 3. And this time
Professor?
I'm going to, what?
Wouldn't that be positive too?
Oh, did I do a mistake? Oh, sorry. All right. So then this will be negative. Thank you very much. That will be negative. 1 plus x to the power minus 4. So it means that now as you realize, I did not multiply by 2 because I want you to see what's really going on before I multiply. So I'm going to go one more term, and then I will see what you have to say. Equal, minus a plus. 2 times 3 times 4. 1 plus x to the minus 5. It means the fifth derivative at 0 is 2 times 3 times 4. Okay, I wrote it so that you guys see the pattern. Do you see anything happening now? What do you think the sixth derivative at 0 is going to be?
2 times 3 times 4.
Right. That's a minus, that's a plus. So the signs are alternate, it's going to be minus. So it's going to be 2 times 3 times 4 times 5. All right. Now, of course, a factorial get into the picture. As you see, this is going to give me minus 2 times 3. That's 3 factorial. 2 times 3 times 4, that's 4 factorial. The sixth derivative is minus 5 factorial. So now let us put the series together and see what we're going to get. So the ln of 1 plus x is going to be equal to f of 0 is 1. F prime at 0 is, f of 0 is 0. F prime at 0 is 1. So 1 times x. The second derivative is minus 1 over 2 factorial x squared plus the third derivative is 2 over 3 factorial x cubed, and then it's a minus the fourth. So I did that 2. Now the fourth derivative is going to be 3 factorial over 4 factorial x4, and then the fifth derivative after that, which is going to give me 4 factorial over 5 factorial x5 minus 5 factorial over 6 factorial x6. I'm going to start writing because I think the pattern is very clear by now. So let us rewrite ln of 1 plus x equal to x minus x squared plus 2 over 3 factorial. If I simplify, what do I get? One, 3 factorial, that's 2. 3 factorial is 6, or 2 times 3. That's
1 over 3.
1 over 3. Minus, watch carefully, 3 factorial over 4 factorial. This is going to give me what? What's the relationship between those two? This is 1 less than that. 4 factorial is 3 factorial times 4. So this would leave me with minus 1 over 4 x4. Now does the pattern continue? It's 4 factorial over 5 factorial. Again, 5 factorial is 4 factorial times 5. And then 5 factorial over 6 factorial minus 1 over 6x6 plus etc. etc. So the pattern will continue this way. So in sigma notation, we're going to have the following. Minus 1 to a certain power, I will take care of that later, x to the n over n. N have to start from 1 to infinity. And now what's minus 1 to which power? If I put n here, since n start at 1, if n equal to 1, I have a minus, so I'm going to put n plus 1 for this to work. Now, for which value does the series converge? This one does not converge for all values of x, that's for sure. If we find the radius of convergence, it means if we evaluate, we find the limit of an plus 1. So you guys, by now, we should be able to do it. So if you find the limit, so this is interval of convergence. Interval of convergence of this term, we're actually going to get 1. We're going to get absolute value of x. You do it, I will not do it, equal to x. So the series converge.
I have
when,
a question.
Yes.
Why is it n equals 1 this time and not n equals 0?
Would it make sense at 0? If I put n equal to 0, I'm going to have a 0 in the denominator.
Oh, okay, okay.
Which absolutely not. Okay, so
All
we
right.
have to be a little bit careful with that. All right.
All right.
So the series converge when the absolute x is less than 1. It means when x between -1 and if we do it carefully, we will realize that, so this is converge for x between -1 and 1. Actually, we can show that it even converge at 1. So it means this equality hold, not for all x's like before, only between -1 and 1. And actually something makes sense here, because if I take x to be -2, watch carefully. If I take even x equal -2, ln of 1 plus x will not make sense anymore. Because at -2, this will give me a negative number. Any number less than -1 will give me negative inside, which makes no sense or whatsoever. So that's the ln of 1 plus x. So now I have the 4 major series that I care about. We have 1 over 1 plus x, which is a typical geometric. We know ex, sine x, cosine x, and the ln of 1 plus x. So those are actually the most important series, and that we use to find everything else we want. So now I will go to your questions and proceed.
I have a quick question before.
Yes, go ahead.
For the -1, why did you do n plus 1? Why wouldn't it be just to the n?
Tell me. Suppose I don't do that. Okay.
Oh, because it's okay. No, it's because if you plug in 2,
right. Yeah. If I plug in n equal 1, I will have -1.
which would be negative. Okay.
Which will be negative. So I have to take care of that. So that's why I added a 1. All right. Any other questions, please? You guys asked very good questions, so please feel comfortable. Okay. So now that we know the basic ones, let's go to the other ones. Some of them we have to find the formula we need, and some wouldn't at -1 make it ln of 0. Elizabeth? Oh, did I do something stupid? Of course. Thank you very much, Elizabeth. Thanks a lot. So Elizabeth said a very important point, and she told me, okay, if I put -1, that was my mistake. She told me at -1, you will have 1 minus 1. So the ln make no sense or whatsoever. Elizabeth is absolutely correct. The equality hold at 1. So if when we study the end point, at 1, I will have 1 minus a half plus a third minus a fourth, 1 plus 1/5, which will be an alternating series that will converge. So my apology, Elizabeth is absolutely right. Between -1 and 1, 1 is included. Thanks a lot. I told you guys ask good questions. So now let me look at the problems that we have. Number 18. So today we're just going to work with those series. I have other things I would like to talk about if I don't have time, which is okay. We're almost done with this chapter, so I want to finish it well. So number 18. Okay. So 1 plus 2x to the -1. And they want the Maclaurin because they want me to put a equal to 0. All right. Number 18, actually, it's easy for the following reason. So f of x is 1 over 1 plus 2x. Why number 18 is easy? The idea is to write the function as a power series. Whether we use the formula, it means whether we use, and I mean the formula, I mean this one. Whether we use this formula, or we use what we've learned in the previous section. It means substitution into known series. Regardless which approach we do, we get the exact same answer. It means the representing a function as a series, there is one series that represents a function, not two different ones. But there are different ways of getting it. One way is to use this formula. Another way is to use what we developed last section, which is like substitution into known series. So now, if I'm faced with 1 over 1 plus 2x, and I want to find its Maclaurin or everything, how do you think I would do? Would I use the formula or I substitute in something we know? What can you say?
You can substitute it into the ln of 1 plus x.
No, this is ln. How can I get 1 plus 1 over 2x? If I substitute into ln, I will get ln of 1 plus 2x. I will not get 1 over 1 plus 2x, which is another series that we know how to write it, and this is totally related to it. And I know you know, but probably you're not. Okay.
Can you use the 1 plus x?
Exactly. Exactly. I go after 1 over 1 plus x. This one we know. This one was the alternating 1 minus x plus x squared minus x cubed plus x4, etc. So this was the sigma minus 1 to the n, x to the n, and this time my n go comfortably from 0 to infinity. I always like to check. At 0, I am safe. At 1, it's minus x, I am safe. And this one converge between minus 1 and 1. Right? Now you can. So now for 1 over 1 plus 2x, then I finish my sentence about you can. So now we're going to substitute 2x for x. And then I will have 1 over 1 plus 2x will be equal to 1 minus 2x plus 2x squared minus etc. It means sigma minus 1 to the n, 2x to the n, and equals 0 to infinity. And now the condition on x. Since I substituted 2x for x, right here, I need the 2x between 1 and minus 1. Because now it's the 2x that has to be less than 1 and not the x itself. Okay, now I just rewrite this in a nice format and I have my series. It would be equal to 1 minus 2x plus 2x squared, which gives me 2 squared x squared minus 2 cubed x cubed plus it's going to be equal to sigma from 0 to infinity of minus 1 to the n, 2x to the n, it means 2x times 2x times 2x and times is 2 to the n, x to the n. And the condition on x would be I divide by 2, a half, and minus a half. Okay. So and that would be the Maclaurin series. In other words, if you take this function, f of x equal, okay, suppose 1 over 1 plus 2x, and start using the formula to get the Maclaurin, we get exactly that. So what do I mean by that? Suppose I compute f of x, then f of 0 is 1, which is the first term. If I compute f prime, so this is 1 plus 2x to the minus 1. So if I compute f prime, I will get minus 1 plus 2x to the minus 2 times 2. So f prime at 0 is minus 2. this term is f prime at 0 times x. So we get exactly the same regardless which approach. Suppose I find the second derivative at x. So suppose I use the formula, which I'm not because I know how to do it without it. I will get minus 1 plus 2x to the power minus 3. And there is a 2 in here. And there is another 2 due to the chain rule. So the second derivative at 0 is going to be minus 2 times 2. Am I right? Why something is bothering me.
Shouldn't it be positive, the second derivative?
Yeah, that's minus 1 plus 2x to the minus 2 times that. So f prime at 0 is minus 2. Minus minus, it's a plus. That's a 2. Oh, I forgot my derivative. I'm sorry. So f double prime equal. There is a 2. That's to forget this 2. The derivative of that is minus minus. That's a plus 2. My apology. 2x to the minus 3 times the 2 due to the chain rule times the 2 that's hanging in here. So the second derivative at 0 is minus 2 to the power 3. All right. Does it coincide with this idea? What should go here? What should go here is the second derivative over 2 factorial. The second derivative is, actually it's a plus here, is 2 to the power 3 over 2, which is 2 squared. And that's exactly what I got right there. So even if I use the formula, I should get exactly the same thing. But the formula is a bit tedious. This one is not tedious at all. Questions? Now let's look at number 36. Number 36. Sine x squared. And the question is, use the Taylor series, find the Taylor series of sine x squared, and this one they want at a equal to 0. So f of x equal x sine x squared at a equal to 0. Right. How would you like to do to find the Taylor series or the Maclaurin? Use the formula or substituting into something we know? Back to you.
Maybe use a formula.
Okay, don't write, let's use the formula. Let's try it. And I want to try it. So you guys don't do, just listen carefully. If I try it, what's f of 0 here? Sine, this is 0. What is f prime? Chain rule tells me the derivative of the outside times the derivative of the inside. F prime at 0 is 0. What's the second derivative? What shall I do? I want you to see the difficulties of it. What's the second derivative? That's a product. I need to use the product rule. What does the product rule tell me? The derivative of the first, which is minus sine x squared times 2x, the derivative of the inside times 2x, plus the cosine of x squared times the derivative, which is a 2. Do you guys see what's happening right there? So the second derivative at 0, this is going to give me a 0, it's going to give me a 2. Shall I stop or shall I keep going?
Keep going.
What do you think?
I think we need to keep going. I don't see a pattern yet.
Yeah, is it hard or easy?
It seems kind of difficult. Can we
It's
just use
tedious.
Sine X?
Absolutely tedious. Using the formula for this particular function is just tedious. It's a nightmare in the making, basically. Because if you imagine what's going to happen here, this is going to give me minus this is going to be 4x squared times this quantity. So I'm going to find the derivative. I have another product rule and then a chain rule here. So it's very tedious to use the formula for this problem. So I'm not going to use it at all. So it's a typical scenario where we're going to use something we know and plus a substitution. So what do I mean by that? What do we know? We know the sine of x. We know that sine of x, because that's the series that I tried to derive them. It's x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x5 and so on. So the sine only keep the odd power of x. And that's basically in sigma notation, it was the following. Minus 1 to the n, x to the 2n plus 1 over the quantity to n plus 1 factorial. And this works for all x. So no matter what x is, this equality holds. So now if I want sine of x squared, which is a highly complicated function, I'm going to substitute x squared for x. And now you see that, then I will get the power series. So what's the sine of x squared? This is equal to, everywhere there is x, I'm going to put x squared minus 1 over 3 factorial. Whenever I have x, I have to put x squared plus 1 over 5 factorial. Whenever I have x, I'm going to put x squared plus etc. So now this is not hard anymore. I don't really have to do a lot of work. So this would become sigma. And my n start from 0 to infinity of minus 1 to the n. Everywhere I have x, it's x squared, watch carefully, to the power to n plus 1, divided by the quantity to n plus 1 factorial. Now, this holds for all x. So it means even if I substitute x squared for it, since it holds for all x, so this is going to be true for all x. Nothing changed in the picture. Now we have to write it nicely. Definitely we don't keep it this way. We write it in a good format. So it's going to be equal to x squared minus 1 over 3 factorial x squared to the power 3. So we multiply the power. 2 times 3, it means x6 plus 1 over factorial x squared, this is x to the power 10 plus so on. So finally, I will get now the sigma notation. Okay. It will become minus 1 to the n over the quantity 2n plus 1 factorial x to which power? What should be the power here?
Oh, wait. I was just confused. So
ahead.
you wouldn't be adding the exponents? I thought when you multiply.
Think about, no. What's the rule? An times am, you add them. Okay, it makes sense because if you have 2 to the power 3, you times it by 2 to the power 4, you have 7 of them. 3 from here and 4 from here, which can I give you n plus n. But if you have 2 to the power 3, the whole thing raised to the power 4. That's a different scenario. It means 2 to the 3 times 2 to the 3 times 2 to the 3 times 2 to the 3. It means how many 3s we have? 4 of them. So it means 2 to the power 4 multiplied by 3. So the rule is you have an to the m, you multiply the power. All right?
Okay, that makes more sense. Sorry about that.
No problem, no problem. As I said, I don't have any question. Now, so what's the power here? What should be the power here?
4n plus 2.
Exactly, it's going to be 4n plus the 2, because you multiply 2 times 2n plus 1, this gives me 4n plus 2. So we're going to multiply the power, and this holds for all x. And that's the representation. So definitely using Taylor polynomial, the formula is absolutely nightmare in this scenario. Using substitution is actually the way to go. So we use Taylor polynomial, the formula, when we cannot relate the function to anything. But once I can relate it to something we know, we have to use what we know. And the power of it is that, like right now, I mean, the way, as I said several times, we can use it is that if you're close to 0, you can sine x squared, which is very hard function, is almost x squared near 0. If you move a little bit away, you can have a better approximation. But this is really to see that near x equal to 0, because when we use the center, like if a is 0, the approximation it will be very good near a. It gets worse as you move away from a. We need more terms as we move away from a. So near x equal to 0, this tells me that the sine of x squared is almost equal to x squared. If I graph this function and I graph this function, they will be almost the same if I am near 0. So this is how powerful those ideas are.
I have a question real quick.
Please.
So for the quiz, if we have a problem like that, so if we just show like how we substituted the x squared into the sine of x, that would count correct. So we don't have to show the work of how we got the sine of x. Does that make sense?
No. Yeah. No, you don't show the work anymore unless I ask you to. Absolutely.
So we can just substitute it into
absolutely. Yeah. And that's really the idea. The idea is we know those basic ones. Okay, we can use them to derive a lot, unless we don't know anything. I mean, unless I give you something, a function that you cannot relate to what you've seen so far, then you have to use the formula. Okay, make sense? All right. So I would like to do, I know that you didn't ask, but I would like to do something that requires Taylor, not necessarily. So maybe actually, let me go back to your classmate before I do that. Suppose I ask you to find the Taylor or Maclaurin series of f of x equal ln of 1 plus 2x. Okay, how would you do it? I'm not going to do it, but I'm asking you. What do you think I will do?
Use the equation for ln 1 plus x and then substitute.
Right, exactly. We start with ln of 1 plus x. We know what this is. We actually, we figured it out. And then you substitute 2x for it. And then you will have the power series for ln. Okay, so now once we have ln of 1 plus x, I can do that. But if I have ln of x, for example, and I tell you find the Taylor at a equal to 1, you have nothing to work with. In this particular scenario, I have to go through the whole process because I have nothing to work with. This is ln of 1 plus x at 0. ln of x at 1, there is nothing to work with. I have to go from scratch. Even if I ask you e to the x, for example, at a equal to 1, also you don't have anything to go with. You have to do it from scratch. So let's do some problem along those lines. So I pick any problem. Let's pick, I don't know. I had decided to look at number 8. No, not 18. Number 27, for example. Okay. And the question is, do you have the function f of x equals sine x? And a is pi over 2. It means I want to find the Taylor polynomial at pi over 2. This time, it means the polynomial now is going to be in x minus pi over 2. Okay, not in pi over 2. So now this is f at pi over 2 plus f prime at pi over 2, x minus pi over 2. So now I have nothing to work with because I need a polynomial in x minus pi over 2. plus etc. Okay, so I'm doing the approximation now. So this is my sine. My sine function goes like that. This is my pi over 2. And I'm approximating the function near pi over 2. That means I'm interested in region right there. I want a good approximation near pi over 2. For this problem, I have nothing to start with because I know sine near 0. So I know sine near 0, but I don't have any idea what's happening at pi over 2. So in this scenario, I have to start from scratch and proceed to find all the derivative, which is usually when a problem like this is given to you, some kind of a pattern will emerge and you will be able to do it. So let's do that. And like last problem, you will tell me where to stop. So at pi over 2, I will get the sine of pi over 2, which is a 1. F prime is cosine f prime at pi over 2 cosine pi over 2, which is a 0. So as I said, I have to go from scratch. The second derivative is minus the sine. So the second derivative at pi over 2 is going to be minus 1. The third derivative is minus cos minus sine, so that's going to give me minus cosine. So the third derivative at pi over 2, which is going to be a 0. And now the fourth derivative is, that's a cosine, so that's going to give me the sine. It means the fourth derivative at 0 is going to be, at pi over 2, which is going to give me 1. And now my pattern is starting 1, 0, minus 1, 0, 1, 0, minus 1, 0. So now let us put the whole thing together and see what we get. So sine x will be equal to, all right, f at pi over 2, which is a 1. F prime at pi over 2, it's a 0, it's gone. F double prime at 0 is 1 over 2 factorial x minus pi over 2 square plus the third derivative is 0. It's a 0. I move to the fourth derivative. The fourth derivative is 1 divided by 4 factorial x minus pi over 2 to the power 4. And now we know that the fifth derivative is going to be a 0. The sixth derivative is going to be a minus 1 because that's how the pattern is building. X minus pi over 2 to the power 6 and so on and so forth. So in sigma notation, this would be equal to sigma. Only the even power are staying. So only the even power are staying. That's my 2n. And then here I have minus 1, and I will take care of the n in a second, and then 2n factorial. And my n will start. It seems to be starting at 0 in this case, to infinity, because if n is 0, 0 factorial is 1, so I don't have issue with that, and that's 1. And my minus 1 is going to be raised to the power n. And that will be the sine of x. And near pi over 2. So it means if I'm interested in approximating the sine, I need a very good approximation, but not near 0, near pi over 2. That will be the best quadratic approximation of the sine near pi over 2. And that would be the to the power 4 approximation, to the power 6 approximation, and so on. Now for the radius of convergence, this one will converge for all x. The 2n factorial, if we do the math, will make it converge for all values of x. So that's the sine of x. So this is a situation where I had no choice but to use the whole picture because I don't know what's sine near pi over 2. I have to do the work. Okay. All right, my time is up. The time is up. So I know that you guys struggled with the homework yesterday. So I hope you can, what I want you to do for tomorrow, not the homework that I've assigned, the new one, I want you to finish the previous one, just to be on the right track. So what I want you to do tomorrow, don't ignore what I've assigned. I want you to finish the problem I've assigned for today. So 14, finish the problem I've assigned for today. And then tomorrow we'll work with the other ones. Okay, that's the one I want you to finish for today. Okay. Any questions before we leave?
So just finish the homework you assigned yesterday.
Yes, yeah, because I looked you guys up and I realized that a lot of you are struggling with it. All right. So I want you to finish that. And then for the following, you do what I've assigned supposedly. So today, finish what I've assigned for today. Okay. Any other questions?